centimeter, some millimeter during that short time. Okay. Or the other one is here terrace X by separating the antenna. So if you separate, the whole antenna is transmitting, but you separate the reception from the first half of the antenna and the second half of the antenna. Right. So there's a short time difference between the front and the back of the antenna. You can imagine it's a very short time difference. But if you have something that in that short time difference is moving a millimeter, right, then you would have a phase difference and you could measure that. And that's, for example, fast-moving cars. Right? Fast-moving cars, going around on the street. They're moving, and if even that's in that short time difference, they are, depending on their speed, but they are moving up, probably a millimeter. That would cause then a phase difference that we can measure in that along track itself. And so by using antennas that are separated along the track, along motion, we can measure motion differences, phase differences caused by within a very short time. So very fast moving objects, and we have some examples on that. For example, a tidal current. I can measure here the very interesting part, the motion of the sea, right? The tidal currents here in that area. It's very interesting because it shows you that that is water. So we have some coherence for this very short time on water, and we can measure here also the motion on water under these circumstances, so that we have a very short time difference, so that the water stays coherent, and we use that. Also, we have the phase difference because this is rather fast moving. So it's a very, very interesting example of how far we can go with SAR and INSAR measurements here. Or another example is then on the cars, on the motion with the long track interferometry, on estimating here the motion of cars. So you can see, and I showed you that before on this example on bridges over water, right? I showed you that example with cars going over bridge over water. We find the cars in the water, and similar here. So this would be the car that we measure. This, you see this red ones. They are displaced. They are put away from displaced away from the road, right? And normally we couldn't find them because they're somewhere mixed. What we can do then, by looking with a long track interferometry, we're looking now at pixels that have a phase difference between them in this very short time, right? And these are then fast moving objects. And now we can identify these fast moving objects, even if they are not on the road. We can identify them by having a phase difference between them. And so in that way, we can here identify all cars moving along the street, which in the other example, we just could identify them when they are on water, because then we have them on this, we can separate them from the dark background, right? And in this case, we do not need that because we're looking at phase differences. But what we need to do that is we need to have the antenna configured in this along track interferometry mode, which is typically not the case, right? So this data is here available as experimental data, as scientific data from the DLR, but it's not like generally available for all areas. Okay. Nevertheless, if you would want to, you could always construct a satellite that's doing that as a standard mode. And there are lots of airborne SAR systems that are doing a long track interferometry and the speed and car measurements as their standard mode, mostly for military interest, because you can detect all moving objects or moving cars and non-cars over large area. So that is of high interest for security and military applications, right? And that's how it's done, basically, by having the antenna in a long track, configured a long track, so you can measure then fast motion instead of very slow motions. Okay, so to have a short summary on DESAR here. So when we are combining, making a difference of two complex values, I measure difference in the phase, right? And we are looking at the phase differences, and we have different things that we do with that. Okay, so this is separated by the baseline types. So let's take a look. So if you have a difference in the angular difference with a cross track, that's inside. We're looking then at topography making DEMs. Okay, so we're interested in differences in the angle. These differences in the angle for different topography will lead to phase differences. Based on the topography, we can use these to get DEMs. Okay, and the other ones, you see, the other ones are delta T. We're looking at time differences. Now, if you have a very short time difference, some milliseconds to seconds, that's what we call them a long track interferometry. And what we do is ocean currents or moving object detection, fast moving object detection. If we have a time difference from days or hours, it's then called differential interferometry. It would be glacier ice fields, lava flows, hydrology. There most of them you would rather like hours than days, because they are moving relatively fast. Right? So that's why we separate them from delta T from days to years, which is still differential, but then we're talking about very slow moving things, so subsidence, seismic events, crustal displacement, volcanoes, these things, they're very slow moving, where we have then millimeter, centimeter per year. That's what we can also measure. That's what we typically measure with the, let's say, the standard differential ISA applications. And then last but not least, by looking at the coherence, right, and at different time, delta time, right, we can see how long does it take for sea surface to decorrelate, and also land cover classification. So we could separate, if we have a wide range of time differences, even including different milliseconds, seconds, days, hours, right? We could different water decorrelation types, but land cover classification, water decorrelates very fast, right? But we can say, well, different lower vegetation decorrelates slowly, high vegetation forest decorrelates fast, urban areas do not decorrelate or extremely slowly. So if you have many images with different delta T's, with different temporal baselines, we can then look at how fast does a pixel decorrelate over time. Quite interesting for land cover classification, especially if you sync it also seasonally. So if you have really many images going over seasons, you have a winter, summer season, or rainy, non-rainy season, and then you look at well, how fast does it decorrelate in winter? How fast does it decorrelate in the vegetation season? When does the vegetation, season begin? When does this crop begin to grow faster? You could really look a lot there, this long time series in terms of land cover classification. And I pointed to that because I also think that is still a rather under-researched area, because I believe now with Sentinel, where we really have that data, where you can go, we have now years of data available every 12 days, so you would have seasonal information. Some areas every 6 days, so you, I think, quite well established some kind of land cover classification over time, which again, I think is under-researched. There could still be more research done in that field. Okay, now that was it from differential interferometry. So we are coming to the next big topic on the permanent scatterer interferometry, which is an extension of the differential scatterer interferometry, sorry. And we are looking here again at motion, slow moving objects like subsidence, volcanic activities, seismology, something like that. But over longer periods, and the goal of permanent scatterer interferometry is to overcome the problems that we have with the INSA. I don't show that slide again, it's boring, you just saw it. Okay, so what are the problems of the dinosaur? Well, that's obviously a typo, that's obviously auto-corrected, and I did not see it. It should mean de-INSA, okay? Right, so I have to change that before I send you out the slides. But yeah, all right, de-INSA, it should mean de-INSA, okay? Okay, so what we have as main problem is the temporal decorrelation, okay? So as soon as we go over a couple of days or months, we lose all correlation over the image. This is a huge problem. So we can't really use the INSA to monitor over a very long time. We want to monitor over a very long time because these elements like subsidence, tectonic motion, we want to monitor them. These are slow objects, we want to monitor them over long periods of time. So that is very important. Temporal decorrelation is really, well, taking away the applicability of the INSA here. Then we have atmospheric effects, right? We do not acquire the images at the same time. We can't because we want to have a difference in time, right? So we have atmospheric effects on it, which makes then the measurements and also the interpretation sometimes quite difficult. So what we do with permanent scatter is we're looking at many images. So not only 2 or 3 images, but we're looking at a rather large number of images, what we can call a stack of images. And then we're looking at single targets. So we're looking at single coherent targets that are not affected by temporal and geometric decorrelation, and we call them permanent scatterers. And we use them then to estimate the atmosphere, right, and remove that. And then we can come to the phase contribution in good accuracy. So what we are doing is, right, in terms of temporal decorrelation, we are not really fixing temporal decorrelation, okay? We are avoiding that. So you see, we are looking only at points, right, that are slightly affected by temporal decorrelation, okay? So we're looking only at a subset of points. We're looking only at those points that do not suffer from temporal decorrelation. So we're not really fixing temporal decorrelation. We are avoiding it by concentrating on other points. Now in terms of atmosphere, we are then actually, we are removing the atmospheric phase. So we're estimating the atmospheric phase and removing that. So this, if you want, this problem we are actually solving, while the problem of temporal decorrelation we are not really solving, we are avoiding. Okay, so let's take a look on how we do that. Right, I just showed you that phase, that slide again. So this is better. Okay, so when we're looking here, right, at this image here, so you see there's a lot of noise on the left side. It's a very noisy image, right? And in the middle, we are only looking at a few points. Like these are the stable points, the so-called PS, the permanent scatterers. Okay, so these are the points that are not affected by temporal decorrelation. And if we're only looking at them, now we see a structure, right? While on the left side it's only noise. If we're only looking at these stable points, we see a structure we can interpolate between these points to get to a deformation signal, or to fringes, right, if you want. So on the very left side, because of the noise, the information is there. You know, it's the same points. These PS points, they're in that noise. You just can't see it, right? Because there are so many non-stable points around it. But if we are finding the stable points, if we're able to do that, and then only looking at them, then we come to extract useful information out of the noise, right? Which you will not be able if we cannot separate them, right? If you don't know which point is stable and which one is not. Okay, so we're looking at those PS points, points that we can observe over long periods of time that stay coherent, right? And we are only looking at the phases for these points, and then we can interpolate these phases and unwrap them all over the image. But the trick is to only look at these PS points. All right, in that, let me see, okay. In that PS point definition, there is one more important part in the definition of a permanent scatterer. So originally, we defined them as being coherent over long periods of time. However, we add one more definition to them. We say also they have to be point scatterers. So we define them as having to be point scatterers. I showed you in INSA the difference between point scattering and distributed scattering. So PS is a point scatterer defined as having only one strong scatterer per resolution cell. So only one scatterer that is so strong that all the background scatterers, there may be more, but from this one scatterer is dominating. Okay, his backscattering is so strong that if there's other small objects in the pixel, in the resolution cell, it doesn't matter. The signal will be dominated by that one scatterer. Now, if we have that, if we also have a point scatterer that has one more advantage, it means we do not have speckle, because speckle is defined as having, speckle noise is defined as having several scatterers in one resolution cell, which then by their coherent, by the interference of the phases, of the return of the phases, they cause that speckle noise. We do not have speckle noise if we only have one strong scatterer in a pixel. Therefore, for PS we define them as being point scatters. So we're looking also that we only look at point scatters. They do not suffer from speckle, so we do not have speckle error in our phase measurements. So we have the measurements of point scatters. And if we go back to the slides, which I still have to send you, so that they actually can go back. If you go back then to the slides from interferometry, right, you will see that we separated distributed scatterer and point scatterer. And for exactly that reason, right, because when we have then a point scatterer, a PS point, we get what we call a deterministic scattering. So we do not have speckle, we do not have speckle noise, we do not have temporal decorrelation. Our pixels stay coherent over the whole time. That is because we define the PS. Like the PS has to fulfill all these criteria to be considered a PS. Right? So we then have a measurement that is deterministic. There is no speckle noise on it, so we do not need to correct for that. We do not need to do averaging. We do not need to do statistics. We do not get an expected value. We get a deterministic measurement, making our life so much more easier and our measurement more precise. So that is the other point of a PS point. A PS, a permanent scatterer, is also a point scatterer. So there's no speckle noise, to make that clear. And for these points that you find, they're stable, they're coherent over time, and they're not suffer from speckle noise. Now from that, we can get to the atmospheric phase screen, right? So we have images taken at different times. So they have APS differences, they have differences of the atmosphere, right? But because we have a number of images, we can estimate that we can interpolate that if we have a dense enough number of, if we have enough points, if we have a dense enough network, right, enough points per square kilometer, what it says here, 5 points per square kilometer, something like that as minimum, then we can estimate them and remove them. And we are doing that because we know something about the atmospheric phase screen. We know that the atmospheric phase screen will change slowly in space, right? So if you go from one pixel to the next, the atmospheric phase screen will be similar. There will not be jumps, right? If you go out in the weather and you walk a bit around, there's not going to be a jump in the weather situation, right? You're not going to have suddenly, strong rain and then 2 meter again. There's no rain, 2 meter again. There's strong rain, right? That is typically not happening. That would be very, very uncommon. Okay, so we can say the atmospheric phase screen is related in space. One pixel to next, it is related. But we also say it's not related in time. So from one image to the other image, there is no relation. We say that because there's a huge time difference between our images, right? There is, like in TerraSite's 11 days. Okay, Sentinel is 12 days, something like that, several days time difference. And from 10 days time difference, we can say, well, the weather from today to the weather in 10 days, who knows? There's no relation. It's unrelated in time. If we have images that have a much shorter time difference, a much shorter baseline, okay, for example, airborne systems or also ground-based systems that are on the ground, that probably take a SAR image then every couple of minutes or every hour. We would say differently, right? And we would also say, well, probably, from 1 minute to the next, even from 1 hour to the next hour, the weather is probably still related. Okay, right? So then we would also say, if we have a situation like that, we could also say, well, it's also related in time. We say it's unrelated in time because the time difference between these two images is rather large. We talk about days. And as we all know, from today, the weather today to the weather in 10 days, that's probably unrelated. Okay. All right, so let's take a look at the processing step by step. PS processing is a large multi-step process. So we start with SAR images, many SAR images. So we would say, as a rule of thumb, at least 20. Okay, better more. Okay, these images are here set in time and the spatial baseline and temporal baseline of these images. Right. So this is quite a lot of images. We then select one master image. Okay, and then we co-register all images to that master image. We then take a DM, right, and then we take the differential interferograms. Right, so we remove the DEM so that we remove the flat earth and the DEM so that we have only the motion left plus DEM error plus atmosphere. All right, then we take the first PS selections. So we take a subset of the PS points. We form then a sparse grid between them. We use that to estimate the atmospheric phase screen. I'll show you soon how we do that. And then we remove it. Right. So first estimate it, then remove it. And then we can do time series analysis for each of the PS points and then get to a displacement field estimation. Right. So you see it's a multi-step process where we use many images, then generate also many differential interferograms to then get to our displacement field generation. Okay. So, okay, let me delete that. Now the first question that comes up would be, well, it's all nice and good what I'm telling you, but how would I know which pixel is a PS point? Right? How can I know that? Right? I look at that noise. Right? I have no way of knowing. And we can do that by looking at many images. Okay, we need a large number of images, again, ideally 20 or more, to identify the stable points over time, over a set of images. And there are many ways to do that. Okay, so there are many approaches where we can say, well, this is a stable point and this is not a stable point, but the standard way in PS INSA processing is the amplitude distribution. So we are looking at the distribution of the amplitude over time. So we are looking here, we want a point that has a high amplitude and a low standard deviation of the amplitude over time. Right? That's also a mean standard deviation rate ratio much larger than 2. So like in this example, the blue histogram. Now why are we doing that? Right? Because actually we want what we actually want is phase stability. What we are looking at is amplitude stability. And the reason is that it's easier. Okay. Now, looking at the amplitude stability, so looking at a point that has a high amplitude and a low standard deviation of that high amplitude is easy and is a valid estimation of phase stability for points that has a high amplitude. So if your point has a high amplitude, if it's a wide point, okay, a strong scatterer, a high amplitude. If this point also has a, a small standard deviation from amplitude, so if the amplitude is not changing much, right, that's a very good indication of a stable phase as well. So for points with high amplitude, that is directly related, in this case amplitude stability is then directly related to phase stability. If your point has not so high amplitude, that relation is not so good anymore. Okay, so we may have points that have phase stability but are not so, do not have such a high amplitude, so are not so wide in your SAR image, right? For them, the amplitude distribution index is not a good indicator, and there are other methods to find such points. But for points with a high amplitude, it is a very good indication of PS, and typically as we are looking at point scatterers have a dominating the scattering in their pixels, so they need to be bright. Okay, you need to have one strong scatterer so that you dominate the background. So in that case, it is a rather logic and meaningful way to analyze here only the amplitude. Again, there is more than one method to look at your PS points, and we talk about these different approaches. And some approaches do also or mainly look at the phase and the phase stability. But the standard way is looking at amplitude stability for points with a high amplitude that have very small standard deviation of that amplitude. We say these are PS points, or actually typically at that stage, at that very early stage, we call them PS candidates, because we are now not sure if they're really stable points, but we say, well, that's a pretty good candidate to be a PS point. Another advantage to do that based only on the amplitude data is that if we do that, we can do that as a very first step and do not need to process the phases yet. So we do not need to process the differential interferograms for all points, right? We could select our PS candidates first and then calculate the differential interferogram only for the sum of these points, so not for the whole image, but only for this PSC, which would save us also calculation time. Okay, so that's one way to identify PS points or PS candidates, right? All right, and then now we are looking at these different phase components. So we are looking here, right? Right, we're looking at height together with over the baselines, and then we have relative velocity average, relative velocity estimation of linear velocity. And there's a temporal difference times the relative velocity of that. We also have nonlinear motion components, right? And also we are gonna have, if we estimate all of them and remove them, we're gonna have these phase residuals, which can be related to the atmosphere, to not corrected nonlinear motion, to the atmosphere, or to noise, right? So this is these phase residuals. I come back to that again to explain you what we're going to do with them. Okay, but just here they're mostly related to, well, elements that are nonlinear if we don't estimate them correctly, or elements of the motion that we do not estimate correctly, the atmosphere, and plus noise. Right? These are the elements that we do not estimate them correctly. Okay. Move my drawings. Okay, so elevation error. So we have an elevation error, right? A DEM error. Again, we remove the DEM, right? We remove the topographic phase estimated from the DEM, but it's not going to be perfect. There's going to be an error. However, the elevation, right, the error of the elevation, that is related to the baseline, right? That is a function of the baseline. So the height, there is the phase related to the height, or from the DEM error, or from the height, as ever you take it, right? That is, have a relation to the baseline. We saw that in the equations before. For the topographic phase, the baseline is in the equation, while it's not for motion. Right? So if we can separate a part of the phase that is related to the baseline, then we separate the part of the phase that is related to topography. Right? Which we can then use to estimate the DEM error and also remove it. Now, the motion, so if we estimate a constant velocity, if we say we have a linear motion, a constant velocity over our image, then we can form a function, right? We know the time difference between each image, okay, from one image to another. So we can estimate, and we can set up a function that says for this time difference with this velocity, the overall deformation would be so many millimeters, and based on the equation that I showed you, that would correlate to a given phase, right? So if we assume a constant velocity, we can again set up such a function because we know the time difference. So we would know for this velocity how much overall deformation would be related after a given number of days between them, right? Okay, right. Let me come here. Okay, let me explain it in step one. Maybe we go back then. Okay, so now what we're doing. All right, let me move my things down. Okay, so we are looking at PS points now. So we're not looking at images anymore. We're looking at points. If you want, we are now looking at a point cloud. Okay, so we're not really doing so much image processing anymore. It's now much more like point cloud processing or topology. So from one point here to another point, we can form like a relation, right? Such a vector. Okay, right? All right. Remember, we are always looking at differences, right? So we're always looking at difference between one point to another point. Okay, so from one point to another point, we can now have a look at the equations to see the difference in height between these 2 points. Right, is this one here, delta H, right, is related to the wavelengths. The difference in the topographic phase, the range, the incidence angle, and the baseline. And this is all we know, right? I mean, we know the range, we know the incidence angle, we know the baseline, we know the wavelengths. So our relation is between delta H and delta the topographic phase. Right. Now, actually, I should not show you the equation like this. Actually, we should solve it towards the topographic phase as a function of the others. Okay, because that's how we actually calculate the common steps. Right. So, for a given height difference, we can calculate the given phase difference. Okay, so this relation we can set up. Similar, right, for a given linear motion, right? So if you assume a constant motion, right, we can calculate the given. Actually, it should also be delta, to be honest. There should be a delta here. We can calculate the difference in motion phase between the one point to the other point. So, given that we can set up a set of linear equations, okay, and solve, for example, these are least square estimations for, toward height difference and linear motion difference between these two. There's one problem though. So we have many images, right? We said we take like 20 images or something like that. It's just a rule of thumb, okay? So if we have so many images and we only have two unknown variables, delta H, right, as a difference in height and a difference in motion between these two pixels, within the two PS points, should be easy to solve. But we have more unknowns, right? So for each image, we also have an unknown here, which is the wrapping factor, right? So we have an unknown wrapping factor. You see that's a factor times the 2 pi for the topography. So how much the topography phase is wrapped between these two pixels. We do not know how many wrapping cycles there are. Similar, we do not know how many wrapping cycles for the motion value there are between these two pixels. And as they are, for each image, they might be different. So we have always more unknowns than equations, right? So we always have an underestimated solution. Okay, we always, instead of an overestimated one, we have an underestimated solution. All right. Okay. However, also underestimated solutions, we still can solve them. Okay, we have methods to do that. All right. So still doable. Now, one more thing I did not mention yet. So we form here a link between two PS points. Yes, okay. Now we estimated here the topographic difference and the motion difference between these two. But there is also, right, the atmosphere. We did not estimate that, right? So we have, before we had the equations of topography and velocity, and we said another phase component would be the atmosphere. We ignore the noise. The flat Earth we have removed by it from the differential interferograms already. So missing part is the atmosphere. And that's now coming to the trick of it all. Right? So we said from one pixel to the next, the atmosphere is changing slowly. So if our two PS points are very close together in space, the atmosphere component that's in between these two pixels, right? That's the atmospheric difference between these two PS points. It's very small if our distance is very small. And so if our atmosphere, if the part of our atmosphere, it has to be less than 2 pi. Okay, much less than 2 pi, because if it's more than 2 pi, then it's more than we can. It's more than in the wrap phase, and then we could not solve anymore because we would be random, we would be ambiguous. But if our atmospheric phase, and the atmospheric phase, you see, it's in here, in the residual, okay, in the what's left unsolved part, that residual has to be much less than 2 pi. Right? If that is the case, then we can solve. So if our 2 points are very close together, and typically we say less than 2 kilometers or less than 1 kilometer, then typically the atmospheric phase difference from one point to that point is the phase residual of that is much less than 2 pi, much less than 1 pi even. So in that case, we can solve for them, right? So the trick is that these 2 points have to be close together, and then the atmospheric phase will be in that residual, but it's so small that we can still solve for the rest. We can solve that. There are different ways to do that. You see, it's an underestimated system. One way to do that is, for example, here using integer least square, because we know A1, B1, these unknown wrapping parameters, they're integers, right? So you have one phase, you have 0 phase cycle, 1 phase cycle, 2 phase cycle, 3 cycle. It's an integer. Okay. Knowing that with integer least squares, we can solve that. For example, we can also solve via periodogram. Oh my God. Right. So basically, like you can make a stupid solution. Okay. What is a stupid solution? Well, you set like a range of acceptable height differences or motion differences between these 2 points. So you'd say from 0 to 100 meter height difference, or minus 100 to 100 meter height difference, minus 50 to 50 millimeter motion difference. Okay, just as an example. Okay, between these 2 points, then you could set up, all possible solutions in that solution space, and you would look for the highest P, for the one with the smallest residual, right? So basically, we always try to optimize this one to have the smallest residual vector, right? So integer least squares would work, setting up periodogram, being very stupid and just go through all the possible values and look for the ones with the lowest residuals. These are all different solutions, right? That do work for you. Okay. Now, having done that, right? We are left with the residuals. Okay. And the residuals that we are left with, right, that is, to large parts, the atmosphere. So we are left with a vector, right? We have here a vector for each image, a vector of residuals that includes mostly the atmosphere plus some noise, right? Plus maybe some nonlinear velocity that we not estimate correctly and some other errors, but mostly the atmosphere, which means we now have values for the atmosphere. We now basically have an estimation of the atmosphere, which we can use. And that's the key element of it. Now, me running out of time a bit. Let's see. Let me still go to the next two slides. So how that all plays together. So that's how we get from a connection between 2 points to estimate the height difference, the linear estimation difference, and the atmospheric vector between them. Okay, so what we are doing is we're starting with these points. Okay, then we form a network between these points. In this example, just a Delaunay triangulation. We could also make different networks or multi-layered networks, you know, with points more far connected and layers of points connected more closely. You can do different things, right? Up to the, you know, it's topology at the end, right? You can use there many methods from topology. All right, we form a network between them. And for each of these connections, we can now estimate, as in the method of the last slide, the height difference between them, the velocity difference between them, and the residuals of them. So basically the atmosphere part between them. So this is the difference here each time along such an edge. Okay, so what we estimated in the last slide was the difference between these 2 points. So it's a difference along an edge, a vector actually, because this vector has a direction, this edge has a direction from there to there, right? Or from here to here, this one has a direction. Okay, so here I give you the height difference. So from that point that I just painted to that point, there's a 10-meter height difference. From that point, that direction is minus 15 meter. And similar, we would have such vectors for the velocity and the residuals. I just didn't show them here, you know, to make the slide not too overloaded. Okay, so for each of the connection, we estimated these values, right? And again, these connections need to be short, right? So we connect the closest points. That's typically so why we use Delaunay to connect the closest points. Okay, they need to be shorter than 1 kilometer, 2 kilometer, so that the atmospheric difference between them is not too big, so that we can estimate them atmosphere free or with very little atmospheric influence between them. All right, now after we did that, sorry, I have to, this always, okay. Now after we've done that, we do estimate, we do define basically a reference point. So in this case, we said this point here is the reference point. Okay, so that's this point here on that side. And then we follow these edges, right? So you see that point here is 10 meter, right? And then you see this one is in this direction is minus 10 meter. So in that direction, upwards is 10 plus 10 meters. At this point, is 20 meter, right? And so on. We follow them through all the points along this network. And now for each point on the network, we have a height relative to our reference point, which we define to be 0. Or if we know the true height of that point, we could also start from the true height of that point and then follow the network. Okay, but typically, okay, we set it to 0. So for each point now, for each PSC, we have the height with relation to the reference point. We're going to have the motion, the velocity in relation to the reference point. And we're going to have the atmosphere residual vector, okay, the residual vector in relation to the reference point. And there's one more thing what happens, right? You see, because we just follow always on these edges, and the differences on the edges is typically not so high in velocity. And height often, depending on if you're in urban area, it doesn't matter, especially the atmosphere, the difference is not so high. But we can also call that whole process here an unwrapping along edges, okay, because we are going along the edges. You see, if we look at the atmosphere, okay, the atmosphere from here to here, we said it's less than 2 pi. Okay, that was like one of our requirements. So that is like less than 2 pi. So from there to there, the unwrapped and the wrapped values are identical if we go along that edge. But now here we start again, right? And we go to the next edge, right? And we have another residual vector here. We can also call this process an unwrapping along the edges. So what we're doing is we also unwrap these residual values here along the edges. So when we go from our reference point then to another point more far away on the edges, okay, that point, isn't that point here, that point on the edge, right? We get then an unwrapped residual vector there with respect to the reference point. Okay, and now this unwrapped residual vector, we're looking at that, we are saying, well, you know, that's mostly atmosphere. So what we just did going along the edges is we just unwrap the atmosphere along the edges, and now we have along the image the atmosphere, the unwrapped atmosphere, which we now can remove. We do one more step though. After we have that, we are doing typically a mean filtering of that vector in space. So we say, well, you know, the atmosphere is related in space, slowly changing in space. So we filter these vectors here in space with a mean filter, with an averaging. And we said it's unrelated in time. So in time, you see we have a vector. I told you we have a vector, which is a vector in time. Between these different images, they have a different acquisition time. So it's a vector in time. We use a high pass filter, an edge filter, right, in that direction. And that is then what we use as atmospheric phase, which we then can remove from all the points. After we removed the atmospheric phase, right, the last step is after atmospheric phase removal, we again do the whole process for all points. Okay, I'm still gonna manage to finish on time. Okay, so we're gonna here from that reference point. Okay, we start the whole process again. We start all over. We throw away all the values we estimated. Actually, at the end, we only keep that atmospheric value. After we remove the atmosphere, we start from that reference point, and then we connect to all other points directly. So even the points far away, we connect them directly, even points very, very far away, right? We would connect them directly because now there is no atmosphere anymore. Okay, we removed that atmosphere. We estimated the atmosphere over these edges here. We removed it. Now we make from the reference point, again, we start at 0, basically. We forget all the values we have. Just after we remove the atmosphere, we connect all of them again, make long connections, and process the values again using, now I want to go back. Yeah, here, again, starting here from making connections. Here, this slide is what I want. Okay, again, then from this point, let's say this is the reference point now. We make connections to other points, but to all other points, and calculate, again, estimate them, again, via this estimation method that we choose for all the points based on that. And now we can do that even for very long connections, points that are very far away. It doesn't matter, right? because we removed the atmosphere. So we do that from the reference point now to all the points. And that's how it works. And that took me a very long time to explain, right? Because that's the critical part of PS Insight. That's exactly the technical detail, how it works. And I made it. Oh no, I'm a little bit late. I'm sorry. Okay, 1 minute late, 2 minutes late. But we're gonna stop here, right? And next time we're looking then much more on what we can do with it. Okay, but this part is very important that you understand how we get there before we show you the applications, what we're gonna do, different approaches, and so on. Okay, so today was very theoretically, but in my opinion, very, very important. So thanks for listening. This is a bit complicated part. Takes everybody some time to understand that. Okay, I will go back again a bit, and then we go through the applications and to different methods, and then at the end, I hope you will understand when I talk about the different methods, because there's more than one way to do that. There are different approaches, and to understand the difference, you have to understand how it's all working. All right. Thanks again for listening. Sishan, do we have questions?
Yes, Professor, we have questions, approximately 10 questions.
All right.
So, okay.
Yeah, sure, we may probably do one, but we are already a bit over time. So
okay.
I will do them again next time for sure. But let me have a look if I can answer one quick one, maybe.
Okay.
Okay. Is it possible to perform time series analysis of landscape using dINSA alone? Yes, basically, yes, there is a process that's called stacking. I think stacking, INSA stacking or something like that, where you just stack these results one after another and not really solve for it like in PS INSA. I will not talk much about that though, also in the upcoming, but we're talking about very different methods on solving PS INSA and dINSA and so on over the next time, because landslides are a difficult topic for the PS INSA. Okay, for several reasons. A, there are not enough PS points. B, sometimes too fast. We come to all of that. We are very interested in landslides. But yes, you can do that. Typically, you have then to stack those dINSA interferograms and then just estimate along that, basically ignoring the atmosphere, which you can do because the landslide is typically rather small. All right, time is up. Just now, one of our participants said it's good that I stop on time, so let me stick with that, trying to stop on time. I'm gonna be next time. It took me a bit more today on that part. Longer than I thought, actually, today. Spent longer time on that. Just a couple of slides. All right, doesn't matter. We still have lots of courses. Dishan, when do we see each other next time?
Yeah, we will actually be here on 23rd, not 22. According to the previous schedule, it should be 22, but we will be here on 23rd, 23rd December.
It's important information that we actually shifted to 23rd, because on 22 there's another course colliding with ours, so we shifted to the 23rd. Okay, so next time is on the 23rd. Do not forget it. All right. Okay, good talking to you. We come back to that. I'm gonna make you understand it. Okay, do not worry if it's not all clear yet. All right, we also come to more application and more beautiful pictures again, so that you know what you can do with it. I know you're all more interested with that. Okay, but you also need to learn the problems and where you can use it and where maybe not. Okay, all right. Was good seeing you. Seeing you okay, online, but still was good. Okay, bye-bye. Have a good day, good evening, wherever you are. Enjoy.
Thank you very much,
Bye.
Professor. Bye-bye. Goodbye.
Bye-bye, Doctor.
Bye bye.
Okay, everyone. So I have actually seen many questions about the slides, and actually also Professor Timo has discussed that. In the next class, we will provide the slides actually before the class, hopefully. Okay, thank you very much, and see you in the next class. We remember that our class actually has moved from 22 to 23. So please remember that we will have the class on the Thursday at the same time. Okay.
Okay, thank you.
Okay, bye-bye. Have a nice day. Bye-bye.
Okay, they can.